Hello everyone, my name is Brian. I make artifacts with AI, and today I wanted to talk about rhyming number theory and iterative building with AI and how I use the two together to create interesting builds. So we wanted to just start here with our basic version of the visualization of rhyming number theory. Here we see all the numbers in the universe laid out on a grid in a spiral-like pattern, starting with 2, 3, 5, 7, classic Ulam spiral pattern, 11, 13, 17. Now, when we hover over a prime number, nothing happens because it cannot be reduced factorially, I guess you could say. But if we hover over non-prime numbers, you'll see it draws a red line to the reason that it is not a prime number. And if we just come up on the side here, it actually lists all the reasons why it is not a prime number. There we go. Now this simulation only goes up to like 1,000, so it's not very helpful. And when we arrange the numbers like this, we're not able to get the effect that we want. The computer gets too chunky with this spiral pattern. So for our next version, we change the nature of the grid, there we go, so that the numbers don't sit next to each other sequentially. They sit next to each other based on the easiness of drawing the tethers. So you can see like 15 is down here, 7 is over here, 9 is over here. On a slider to the right, we can control the density of numbers, and since we arrange this numbers on the new grid, we can actually move the slider up to 5,000. And we can fit 5,000 on the screen, although it gets too blurry. There we go. So here at 2,800 numbers, we can see on the bottom left, the computer does the calculation to determine if it is a prime number or not. And it tells us, is it a rhyming number or is it not a rhyming number? Boop, boop, boop. You see, these are all lovely rhyming numbers, any even number, etc. Now, for the computer, drawing actual numbers on screen, the limit, it wants to stop at like 5,000. And even then we lose the functionality, or some of the functionality. It becomes a bit incoherent. So we switch over to an artistic view only. We can zoom out. And here we have the same concept, just arranged without the numbers. And so you can see we have 12,000 different particles on screen, each representing a different number, either rhyming or non-rhyming. But since we're not actually displaying the numbers on the surface, they're just existing underneath, we can go to the slider and raise it from 12,000 over to 50,000. So this way, now we can swoop down here and see the number 36083 is a prime number. So it is a non-rhyming number, but here 37070 is a rhyming number. The factors are 2, 5, 11, 337. So yeah, by eliminating the need to display the actual numbers and replace them artistically, we are able to display 50,000 instead of just 5,000. So 10 times more just by hiding what the number is. And this spiral shape is a little bit more intuitive than like this weird stacked grid the computer invents just to try and make sense of all this. It makes this stacked grid just to be able to do the tethers. But to avoid all that, we can just switch to a beautiful little spiral and cute little nodes that shine. Now, breaking away from just the visual aspect of rhyming number theory, we can, we have an analytical, we have an artistic visual, but we want to switch over to an audio one. So now we spin off another concept of the rhyming number theory audibly. And I'm not sure if you'll be able to hear this, but we'll give it a shot. Doopy doop. let's do the sequence a little higher and hit play. Where are you? There we go. So for the audio version of rhyming number theory, prime numbers are played as single notes, and then rhyming numbers are played by chords, and the chords are invented based on the rhyming nature of it. So if it divides by 2, that is a certain chord. If it divides by 3, that is a certain chord, etc. And then prime numbers just remain just pure tones. And so now we have analytical, visual, audio, and we kind of want to synthesize it into a final concept. There we go. Which we have this new tool. And I'll just do a quick tour. It has a play button, various layman translations, tempo control, global reset, and then on this side, the different mapping engines. We could do the parallax, the classic spiral, or the H gravity. We can trace the connections and capture PNG. We love that. So what is this doing? Now, if we hit play, there we go. We're going to see dots forming. And then connective tissue is made. So, the green dots in this display are non-prime numbers, and then the purple dots are prime numbers. And this is just a classic Ulam spiral pattern. The numbers are increasing from 0 up to infinity, and we're just arranging them in a spiral pattern and attaching a simple tone or a chord to the sound. And this is kind of the intuitive way to present the prime number concept, because the spiral introduces certain patterns that mathematicians find all kinds of interesting, but we are also interested in the rhyming number theory just by itself. There we go. Let's reset this. So that's a classic spiral. There are several different ways of populating those dots on screen. There we go. And when we talk about trying to randomize them based on rhyming number theory, see here, we can change where the dots populate on the screen. Yes, there we are. So in this next one, we'll see what happens. Composite or primes, so in this one, the prime numbers are going to form an outer ring, and then the non-prime numbers are going to populate inside that ring. Boop. Wait, let's start that over. There we go. So you see, in this one, instead of forming the spiral pattern, the prime numbers form a ring on the outside of this, and then the dots are trying to populate just using the ring as kind of their guide. There we go. And, step over to the right, we can see that it is actually doing the calculation. Let's see if we can pause this. Pure tone at 467. Rhymes 476 to 17.7. There we go. And the computer is learning the limits of where it can draw the dot. And so now, as it begins to understand its place more, it'll start forming dots outside of the constraint. And I wanted to take this idea further and eliminate just the ring concept, but keep the concept of the dots kind of learning where to place themselves as time goes on. So we're going to reset. And we have our third option. Remember, we have the classic spiral. We have the H gravity where it forms the ring. And now the parallax. This is the trying to achieve true kind of randomness with rhyme theory. Just see how that one goes. So this one, the one's going to populate it based on parallax rhyme theory. We're going to reset. Let's just do a full reset. There we go, parallax nebula. So we'll see how it populates this time. Boop. Actually, I'm going to start that over. I don't want those tissues cut off. There we go. Okay. So in this one, the prime numbers don't form the ring on the outside. They just get placed more randomly. But you see, early on it starts a tight circle. And then as it learns the limits of the screen, it is able to form a larger circle. And I feel like with this distribution, we are able to get the randomness that I wanted of purple, purple, green, purple, green, purple, without forming like a circle, without forming a spiral. The idea is to just get the most random placements on the dots that I can. But by doing so, I make it especially deterministic, I suppose. But yeah, so this is just a evolution of this concept of iterative building with AI, taking a concept and building upon it and kind of seeing where it leads you. You'll remember we started off with the most basic version of a rhyming number theory concept. Just draw tethers to where the numbers rhyme, which is kind of a universally understood concept and pretty easy to grasp. But then how do we take that? How do we fit more? How do we get more numbers on screen? How do we color the tethers so they're telling us something useful? How can we get the computer to think about numbers a different way than just 1, 2, 3, 4, 5? Because for the computer, they don't have any emotional attachment or weight to the numbers themselves. It's humans who kind of endow that, like 40, We don't need to see all of these connective lines to know that 40 is not a prime number. Anybody can look at 40 and just know it's divisible by 4, it's divisible by 10. We don't need to draw these connective lines, so we can just cut them off. 168, a little less intuitive, but it ends in an 8. It's divisible by 2. In our thinking, we don't need to draw those lines, but the computer does. You know what I mean? The computer doesn't think of 66, execute order 66 as a particularly impressive number. But humans, we love 66. We love all sorts of numbers that rhyme. 66 rhymes with 6 and 11. It's easy to break it down into 3s and 2s. We can turn it upside down and it's 9, 9. We can do a lot of fun things with these numbers. But the computer just thinks, 2, 258, 66, 322, 18. It doesn't attach significance to the numbers unless we give it. Here's little baby 6 connecting over to 66 and all the other. And then further refining the idea of rhyming number theory, the idea of chords and not chords. We can have the computer think of numbers not sequentially, but rather as just, do they rhyme or do they not rhyme? And let's make music out of it, So, where does this go next? I guess deterministic dot generators that look like eyeballs. But other concepts as well. For instance, we can gamify the situation and come up with a little asteroid shooter. And here we have a enemy floating by. It's a big number 30. What do you think's inside that enemy? What is going to be very, very satisfying for a human to see? 15, 3. 15, 2. Get rid of the 2. 15. Come on, what do you got? What do you got? 15. Come on. God, it's hard. I'm trying to break 15 down. What do you think's going to be in there? Come on, maybe it's invincible. Every day with these. All right, let's find a bubble to pop this for. Okay, inject mass. There we go. Here we go. What's up, buddy? Boop. Bah. Oh no. There's too much prime factoring going on. Oh no. All the prime factors. How high can we make this asteroid bubble pop game go? 1,000,000 bajillion? Stick around and find out. Thank you for joining me and hope to see you again soon.